Welcome everyone. This is Dr. Wortel doing a video on Worksheet 7, as you can see here. So let us go to the first question. So we consider a curve given by the solutions of the following equation, and we have to explain why this curve can be represented as the graph y equals g of x for a differentiable function g near the point 1, 1, and we have to find the derivative in the point 1. Of course, in such a question we want to use the implicit function theorem, which tells us that we have to rephrase the problem in a function of the form where fxy equals 0. So, well, let us say that we have our curve C, which is all the vectors x, y, such that this equation is satisfied, and we want to rewrite it in the terms of a curve where the fxy equals 0. So what we will take is our capital Fxy is simply the function x squared minus 2xy plus 2xy squared minus 1. And if we do this, we see that our curve C can now be written as the solutions of all solutions of the equations where fxy equals to 0. So this is the correct setting for the implicit function theorem. What else do we need? Well, if you look at, in this case, theorem 90 in the course notes, we need the partial derivatives of capital F. So let us compute those. So the derivative with respect to x, that's going to be 2x minus 2y plus 2y squared. And the derivative with respect to y is, so that's a constant, so we get minus 2x. Here we get 4xy. Okay, so we have the partial derivatives. One of the requirements is that they are continuous. And these certainly are continuous, because they are polynomials. Which I will abbreviate like this, and by chapter 2 we know that polynomials are continuous. So this is one requirement of the theorem done. We need to have continuous first order partial derivatives. For what else do we need? We need that the function at the value 1, 1. What is that? That's going to be 1 minus 2 plus 2 minus 1. That's actually equal to 0. So that's another condition that's satisfied. And then the third condition is that we need the derivative, y derivative in the point needs to be non-zero. So let us compute this. We get minus 2 plus 4, which is equal to 2, which is not 0. So these are all the conditions, and just for completeness sake, we will need this later. Let me also compute the derivative in the x direction. This will be 2 minus 2 plus 2, which is also 2. So now all the conditions are satisfied, so now we can invoke the implicit function theorem. So let's say by IFT, which is implicit function theorem. So in this case, this is theorem 90 in the course notes. We know that the equation fxy equals 0, which describes our curve. I already explained this. This defines y as a differentiable, which I will abbreviate like this, as a differentiable function of x near the point 1, 1. So we don't have to be more specific than this. So the full theorem in the course notes explicitly define what this means, but in these kind of exercise it's enough to say this. And now the last thing that we have to do is compute so differentiable function, let's say function g. And now we have to compute the g prime of 1. So according to the formula, this is equal to minus fx in the point 1, 1 divided by f sub y in the point 1, 1. And that is equal to 2. That is also equal to 2. And so the final answer is that it's equal to minus 1. And that ends the explanation for the first exercise. Let us continue to the second exercise. So we have a certain gas which satisfies a law. So here P is the pressure, V is the volume, and T is the temperature. So there's some kind of relation between these three. And what we're interested in is how does the temperature change with respect to the pressure. So if the pressure changes, how does the temperature change? And also if the volume changes, how does the temperature change? Okay, so as in the previous question, I will not explicitly write it out like in the previous question, but we want to rewrite this in a function such that the function equals 0. So one thing that we can do is we can define the function now, and now our variables are simply the three things, so the pressure, the volume, and the temperature. And we could take PV minus T plus 4P over T squared. Right? In that case, this equation here is equivalent to the equation FPVT equals 0. And that is what we need. Because the second one is the setting of the implicit function theorem. In this case for more than two variables, because we have three, we have P, V, and T. Okay, so as before, let me start by computing partial derivatives of this function capital F. So let's first do the partial derivative with respect to the P variable. Well, that's equal to V. T is a constant if I differentiate with respect to P. So we get 4 over T squared. Now let's compute the derivative with respect to V, because I will need them later. That's going to be equal to, well, PV differentiated is going to be equal to P. And nothing else depends on V. So then we're done, and the derivative with respect to T is going to be equal to minus T is minus 1, and then we have 4P over T squared, so that's T to the power minus 2, so we get minus 2 times T to the power minus 3. So we get minus 8P, because 4 times 2 is 8, over T to the third. Okay, so as before, we see that they're all of these are continuous, at least on their domains. This follows again from what we did in chapter 2. And the domains of all of these, well, let's say the domain of capital F is where T is not equal to 0. And that's good because in our case T is equal to 2. So all these things are continuous on their domains. So what else do we need? So we need the partial derivatives in the point. What is the point? So P and V is equal to 1 and T is equal to 2. Okay, so let's do this. V is 1, so we get 1 plus 4 over 4 is equal to 2. What's the partial derivative with respect to V in the point? That's equal to P, and P is equal to 1. And the partial derivative with respect to T. Let's see, that's P is 1 and T is 2, so we get 8 over 8. So we get minus 1 minus 8 over 8 is minus 2. Okay. Okay, so now let's stop a moment and think about what we need. So what we want to calculate is the derivative of T with respect to P. So we want to know how T changes with respect to P, and also how T changes with respect to V. So to do that, it makes sense to have T as a function of P and V, because that's what we want to calculate the derivative of. So this is what we want to do. Let's do this in a different color. The goal is to write T as a function of P and V, right? Because then we can take derivatives. And then if you look at what we need is that the partial derivative of f with respect to t is then not equal to 0. They're all non-zero, so that's good, but at least this one is non-zero. So now we have again checked all the conditions, so now we can again apply the implicit function theorem. In this case, it's of multiple variables, so that's 92. We have that t is a differentiable function of p and v near 0.112. And again, we don't have to be more explicit, because the only thing that we need to compute is the derivatives. So now it remains to compute the derivatives. So if you look at theorem 92 in the book, it also gives you a formula on how to compute the derivatives. And so the dt dp in this point, I will not write down what point it is exactly, but it's going to be equal to fp, sorry, with a minus in the point 112, divided by ft in the point 112. And this is equal to, the fp in that point is equal to 2, and the ft is equal to minus 2, so this is equal to 1. And then the second, we need to compute the derivative with respect to v in the point. So that's equal to minus fv in the point divided by ft in the point, which will give us 1 minus 1 over minus 2 is equal to a half. And that ends the second exercise. Okay, let us continue with the last exercise, the third one. So this is an exercise where we apparently cannot use the implicit function theorem. So first we need to explain why we cannot use this. Okay, so let's start by A. Well, let's say, what would we do if we would try to use it? Well, we would compute the derivative, and we need that the derivative with respect to the y variable is equal to 0, is not equal to 0. So what's the derivative with respect to the y variable? Sorry, the partial derivative with respect to the y variable. Well, that's equal to minus 5 y to the fourth. And here we see that if we plug in the point, which is 0, 0, we get 0. Yeah? And the implicit function theorem, one of the requirements is that this derivative is not equal to 0. Yeah? So here we see that, let's write it out, we cannot use, implicit function theorem because this derivative is equal to 0, and the implicit function theorem tells us that it only works if the derivative is non-zero. Okay, so let's take stock for a moment. So the implicit function theorem gives us certain conditions under which we can write y as a function of x. So now that we cannot imply the implicit function theorem, you might think, well, in that case, y cannot be a function of x. But in exercise B, we are asked to show that even though the conditions of the implicit function theorem are not satisfied, we can still write y as a differentiable function of x. So what this is showing is that the theorem is not an end-all. It does not solve all the problems. Sometimes you can solve the problem, but sometimes the problem cannot be solved by the theorem. It can be solved by other methods. So, okay, now we have to argue that this equation does define y as a differentiable function. And the first statement that this equation is easily seen to be equivalent to the equation y to the fifth equals x to the power 15. And now we get an idea. We want to write y as a function of x, so let's take the fifth root of that. So if we have this equation over here, what we could do is we could take the fifth root on both sides of the equation, right? If an equation is satisfied, we can take the fifth root on both sides of the equation. And now the fifth root of y to the power 5, that is equal to y. So this equation is the same as saying that y, and this is equal to x to the third. Okay, so here I should make a comment in red. Where shall I do this? Let's do this over here. Why is this equation true? Because it is not, let's say we start with the equation y squared is equal to x to the fourth. Well, and again, we can take the square root on both sides. So instead of the fifth root, we take the square root. But now the square root of y squared is not equal to y, but the absolute value of y. Right? And the square root of x to the fourth is the absolute value of x squared, but that's the same as x squared, because it's always positive. And the reason for this, that the absolute value of y squared is, sorry, that the square root of y squared is the absolute value of y, is because if I want to go back, if I take a number and I square it, it will always become positive. So therefore that is the reason that we get the absolute value of y. And that is the reason why if you take a square root, which is the inverse operation, you will always get a positive number. Because, yeah. But so if we take a positive, if we take a square root with an even, how shall I say this? So the fifth root, that would be an odd square root. So if I take an even square root, so I shouldn't say square root, an even root. Sorry. So this 5 here is an odd number, so that's an odd root. However, here we have a square root which has a 2, so that's an even root. If I take an even root, I will always get the absolute value. But if I take an odd root, I don't get the absolute value. And the reason that if I take a negative number and I raise it to an odd power, I get a negative number. Whereas if I take a negative number and I raise it to an even power, I get a positive number. This is the reason why it works like this for odd powers, for odd square roots, because the inverse operation, which is raising it to an odd power, preserves negativity, and therefore we get just a y and not the absolute value of y. Okay. So we see that if this, let's do it in blue, we see that if this equation is satisfied, that equation is satisfied, right? Because we have this arrow over here. Now conversely, if we have this equation, then we can simply raise both sides to the power 5. And that's x to the 15. So in other words, if this equation is satisfied, that equation is satisfied. So now we've shown that this equation implies that equation, and we've also shown the converse, that that equation implies that equation. So now we've shown that the two equations are equivalent, right? So y to the 5 equals x to the 15. The solutions to this equation are exactly equal to the solutions of this equation. The two solution sets are exactly equal, therefore we may as well replace the first equation by the second equation. Right? Whenever you want to argue like this, that a certain equation is equivalent to another equation, you need to show that the solution of the first equation is a solution of the second equation, and conversely that the solution of the second equation is the solution of the first equation. And now we're basically done, because, well, now we've written y as a function of x. And then, of course, the final thing that we have to do is compute the derivative, which is just 3x squared at the point 0 is just 0. So in this case, we can easily compute the derivative. And again, the point of the exercise is to show that sometimes you cannot use the implicit function theorem, but you can just see by hand that indeed y is defines a differentiable function of x by hand in this case.